And hello, and welcome back to OneClass in our live stream of this is Chemistry 11, the SCH3U in the Ontario curriculum. Again, my name is Joey. I'm going to be your chemistry teacher for this session. Just a little bit about myself before we get started again. My name is Joey. I'm currently a intermediate senior division teacher studying at York University in Toronto. My subjects of interest are science and chemistry as well as music. However, I'm planning to get my math teachable further down the road. Just a little bit about OneClass if you're tuning in for the first time. OneClass here is a online kind of site that's developed these videos of online lessons, and they're free online lessons and videos for students, especially in the secondary school level studying mathematics or in chemistry. And in chemistry, and it ranges from secondary school level to the college level and the university level as well. So if you're tuning in for the first time, thank you for watching. And I hope you can kind of get something, get out learning from the teachers here, because we have such a great team of teachers at OneClass. So I hope you get some learning done today as well. If you're a student, I welcome you for the first time. You can kind of see if maybe this may be review for you. This could be for you looking ahead or just catching up. Whoever you might be, I just thank you for watching the stream. And yeah, amidst the COVID-19 closures, OneClass is kind of actively searching for teachers and creating these videos so that there's some online resources for you to proceed with how to continue the rest of your school year. So that's kind of our goal as OneClass. So let me just get started with our lesson today. We're picking off, this is Chemistry 11, SCH3U. We're gonna pick up on where we left off, which was periodic trends. So we have here, this is what we talked about last week. Again, we only do chemistry once a week, so I always love to do chemistry, which is great. What we talked about last week was the topic of what we did last week was we did this topic of isotopic abundance. So remember recalling that we have something called isotopes, and we did a bunch of sample problems with that. I think we did 3 or 4, where we talked about isotopic abundance. So if you had an element, say like carbon 12, which is the which is the isotopic abundance of carbon because it has a mass of 12, and if we had carbon 14, for example, so it's still carbon, but has a different number of neutrons. And what we could do is we found a formula for average atomic mass. That's what you see in our periodic table. So let me just bring this up. Periodic table. That's what you see when we bring this up, right? So this is our periodic table, and the masses here are the average atomic mass. So average atomic mass of carbon is 12.011. So we did that last week. We learned how to calculate the percent at which it occurs naturally, and we also talked about the average atomic mass. So those are the 2 topics we covered last week. We also covered modern atomic theory, and we also did one of the trends. We did atomic radius, and I told you this was the most important trend. So let me just rewrite what we did last week, because we're gonna always refer back to atomic radius. So this is important. So atomic radius, and I defined atomic radius as how big the atom is, right, or how size of the atom. And we talked about the 2 trends, right? The 2 trends that exist is if it goes down a group. So down, remember, a group is vertically, right? So down a group, it would increase, and then across a row or period, this would decrease, right? So let me do increase and decrease in red and blue. So this would increase if it's going down a group, and then decrease if it's across a period. So we talked about those two things, and I gave you an example, right? So for example, lithium and sodium in this case. Lithium here, if I drew the Bohr-Rutherford diagram last week, there's 2 shells, right? The first shell exists with the 2 valence electrons, and the other one with the second valence electron or valence shell has 1 electron, right? So this would, and if I compare that to sodium, it has 3 shells, right? So it's much bigger already. You can see the rings like just increasing, right? So again, that's kind of increasing atomic radius down a group. And across the period, I believe I compared fluorine and neon. So these two elements here, and one has 7 valence electrons and the other one has 8. And the shells are different. They're all in the second energy level, the second shell, right? So the reason why it decreases across a period is because of this effective nuclear charge right here. Because if we have more electrons over electrons and if we have the same number of protons, what it does is the protons kind of draw the electrons towards the nucleus. Because I told you that positive and negative charges attract each other. So that's why we have this concept of effective nuclear charge. And what that is just the attraction between the nucleus and the electrons that hold it together. So it wants to draw it in, hence why the atomic radius decreases. And these two concepts are very, very, very good. You need to know these two concepts before we go into these next concepts, such as ionization energy and whatnot. We briefly talked about ionic radius, but ionic radius, as you can probably infer, is the same thing as atomic radius, but it refers to the ions, right? So let me just write on ionic radius for you. So ionic radius. So it's more so just this is the same thing as atomic radius, but it's only referred to ions, right? So instead of going, there's a specific trend, but it's more so comparing ions together, comparing ions and non-ions together. So positive ions, such as cations in this case, are generally smaller than the atoms, right? Than atoms. And what we did was we compared lithium plus and lithium together, right? Lithium plus has lithium itself has 2 shells. Lithium plus, I got rid of 1 valence electron, which means I got rid of the last shell. So it only has 1 shell, so it's a much smaller, right, than this atom. So positive cations are have a difference in shell size, so hence they're smaller than their atoms. So I used Li versus Li plus as my example. And then anions, so the negative ions, are bigger than atoms. And I use the example of F versus F minus, right? And how fluorine has, again, 7 valence electrons in its second shell. F minus has 8 valence electrons. So if it has an imbalance of charges, right? I have, for fluorine, I have 9 protons and I'll have 10 electrons. So it's an imbalance of the negative charge. So it's going to tend to pulse ever so slightly away. And we can see that in our figure 7 and figure 8 of these diagrams here, how fluorine is slightly bigger. So this is a general trend again. And this is for ionic radius. So it's just a little review. What we're going to do is we're going to move on to the other trends. So we're going to move on to this topic of ionization energy, and then we're going to talk about electron affinity and electronegativity, which is actually not here, but I'll talk about that as well as we go towards trends. So let's do this topic of ionization energy. So this is ionization energy. And what this is the ionization energy, as you can see from this kind of note here that I have, it's the amount of energy required to remove an electron from an atom or ion in the gaseous state or gaseous state. So what that is you kind of have X here. So I have this kind of chemical equation here, and we learned about chemical equations in grade 10 science. So I'm going to write this for you. So this is X in the gas state plus, and the IE here just means ionization energy, and the 1 here means the first ionization energy. So don't worry about the terminology yet. And this is because I get a cation and I get 1 electron. So what it is, ionization energy in this case, is I'm removing 1 electron. So the amount of energy, so this is the IE here, IE1 here is the ionization energy. Oh, sorry, energy, not element. Ionization energy. X here is our element. So it could be lithium, hydrogen, etc. element. And then this here is, it's going to remove 1 electron, right? So so this is the electron removed. Electron removed. And this one here is the cation of the element, right? This is the cation of element. So that's how we kind of read this chemical equation here. So again, ionization energy is the amount of energy to remove one electron. So we really, really care about this energy here. This energy, what we're solving for. This is the energy we're solving for. The amount of energy that I need to interact with this element or to react with this element so that I remove this one electron. This is being removed from the element, right? So that's the definition here. So I'm going to write that down. This is amount of energy to remove an electron is the kind of definition of ionization energy. So let's I'm going to ignore this note here, but let's figure out, okay, ionization energy, if it's the amount of energy to remove an electron, which ionization energies would have the least amount? So if I look at my periodic table, what elements here have a very low number of valence electrons so that if I don't need a lot of energy to remove it? So take a minute. If you're at home, feel free to type in the chat and to answer my question here. But my question is, which elements or which groups specifically would have the least amount of ionization energy that I need to remove an electron? Remember, we define ionization energy as the amount of energy to remove an electron. So which group would require the least amount of ionization energy? So if you're in the chat, let me know your thoughts. Then we'll take it up in about a minute or so. So think about the definition of ionization energy. Think about it's the energy required to remove an electron, right? So which elements want that electron to be removed? That means you don't need a lot of energy to remove it, right? So that's kind of the logic here that I'm trying to convey. I don't need a lot of energy to remove one of these electrons, right? So if I'm only removing one electron, which group of elements has the least amount of ionization energy? In this case, it would be group 1, right? Group 1 here, lithium, sodium, potassium. This is my alkali metals, right? So my alkali metals, I'll write this in black. Alkali metals require the least amount. Alkali metals require least amount of energy, right? Or of ionization energy, sorry. And that's because they already have one valence electron, right? So we know that they have one valence electron, and it wants to get rid of it, right? It wants to become that stable octet rule, the stable octet that we talked about before, right? And that you've been talking about. So one valence electron, which means we don't need a lot of energy. So low IE, right? Because it wants to be stable, right? So this is alkali metals require the least amount. So what would require the most amount? The most amount would be obviously the opposite of the spectrum here. I have my noble gases would have the most amount of ionization energy. So this here was alkali metals. So I'm going to underline that. And then obviously my noble gases. So noble gases, which have 8 or a full octet or a full shell of electrons, will require most amount of IE. This is the first ionization energy. So I'm going to define that first ionization energy. So I'm just only removing one electron here. And the reason why is that they have they have stable octet, or you can say have stable energy levels. So if they're already stable, they don't want that electron to go away, right? Otherwise, it makes it unstable, right? So if they have stable energy levels or stable octets like that you might be familiar with, then I need a high amount of ionization energy to pull that away. So that's noble gases. So these two are, so again, using this logic, what we can define is we can define a trend here, right? So what is our trend? So as we go, so if we define this here, so we can define a trend here, and here's our trend section. So trends of, this is ionization energy. And what we can say is, we can say that the trend as we go across a period, so across a period, it would increase, right? It would increase as we go across a period. And I told you why it increases, right? Because of my two examples here. Alkali metals require the least amount of ionization energy. Noble gases require the most, right? So as we go from this side, as we make our way across the period, it's going to increase the amount of ionization energy. So these ones are obviously the least amount, and the noble gases with the most, and it would increase as we go from left to right. So it increases as we go across the period. And then, what about down a group? So down a group, it would actually decrease, and I'll do this in red. It would decrease. And why would it decrease as we go down a group? And I'm gonna take sodium and potassium again, my alkali metals here, which require the least amount. So why does potassium require an even less amount than sodium? And I'll draw the Bohr-Rutherford diagram for you, and this actually goes back to atomic radius, and I'll show you why that is. So Na has a first shell of 1 and 2. The second shell is full, right? 1, 2, 3, 4, 5, 6, 7, 8, and then our next shell here's 1, right? I did that right? Good. And then potassium is the same thing, but it's bigger, right? So 1, 2. This is a stable one here. And then another stable one. Sorry. Or another shell here. Sorry, not stable. Another shell here. And then our last one here is simply 1, right? So as you can see, potassium is bigger than our sodium here. But why does our ionization energy decrease as they go down a group? Remember, this is sodium here, and this is potassium here. Why does it decrease as I go down a group? Well, it decreased because I'm looking at the trends of ionization energy. Remember, if I defined ionization energy as the amount of energy to remove an electron from the element. So I'm going to remove this element, or so this electron here and this electron here, right? So it is much easier to remove an electron that's further away from the nucleus. And this is why it goes back to atomic radius, because it goes back to this idea of effective nuclear charge. The distance between the positive nucleus and the electron here is greater in potassium than it is in sodium, right? Than this distance here. So it means that the traction between the nucleus and the nucleus in both sodium or in potassium, and this valence electron, the single valence electron at the outside shell, is much further, right? The distance is much further, which means it's the forces between the traction between these two things are weaker, right? So I'm right here. Attraction is weaker. Less, or I'll say less attractive, because further away. You can think about my example here is you can think about your if you have a significant other at home, if you're dating or in a relationship or something like that, you can think about, because they're further away, you are like less likely to see them, right? You're not as you can say you're not as attracted to them as they are far away, or if they're as they are close to you, right? So you're more attractive, or it's more there's more attraction when you're closer to that person than if you were further away. So that's kind of my little side thing there. But it's less attractive because it's further away, and this distance here in sodium is slightly more attractive because it's closer, right? So slightly more attractive because closer, or slightly closer in this case, but because it's further away from the nucleus, they're more loosely held and easier to remove. Right? It's easier to pick off this electron, in potassium, than it is in sodium. And so that's why my ionization energy in this case, or in this example here, between sodium and potassium, as I go down a group, it's going to decrease. It takes much less energy to remove an electron that's further away than it is if it's closer to the nucleus. So this here, I'm gonna right here. This here becomes more stable as I increase the electrons in the shell, and then decreases because further away. Distance is further away, or valence, or actually electron is further away from nucleus, so that it's going to the ionization energy is going to decrease in this case. So that's all, and that's fine and dandy for transitive ionization energy. So this is the first ionization energy, which means there's something called the second one, and the third one, and the fourth one, and etc. So let's talk about what the second ionization energy is, and it's actually the same. It's a very, very similar concept. So I'll show you what it is. So this is a second ionization energy. And it's actually using the exact same concept as our first ionization energy, but instead of removing one electron, we're going to try to remove the second electron from the cation. So basically, you have here, you have something like, it's going to remove the second electron. Sorry, the second electron from that state. So for example, if I had, let's do beryllium. So for example, let me define this first. This is the ionization energy. So IE2 is a second ionization energy would be needed to remove a second electron from atom. So let's look at beryllium, for example. So Be here, beryllium has one full shell, and the outside here has two valence electrons, right? So 1 and 2 here. So for beryllium, the first ionization energy is slightly greater, right? It's not as small as the first ionization energy for alkali metals, but for beryllium, the first one's a little bit more tricky. It's going to be higher than the second one, right? Because beryllium doesn't really want to remove the first electron in this case. Let's say the first electron would be this one here. It wants to get rid of it, but the second ionization energy is much lesser, much smaller than the first ionization energy, right? Because once I remove this first ionization, so the first ionization energy is this one, IE1 here. Once I remove this first electron, it becomes kind of like lithium, right? Where I only have one more valence electron. I only have this guy here. So the second ionization energy energy is very, very small, right? Because it takes me very, very little energy for me to remove this one here. So this is the second ionization energy. So in this case, I'm going to have the first ionization energy of beryllium is slightly larger than the second ionization energy of beryllium. So that's what this is. It's removing the second electron from the atom, from this atom here. So I did this in red here, and I did the first ionization energy in blue. So let me just do some blue. So this is IE1. Cool. And this diagram here just shows that if I had an atom, let's say beryllium, if I add a first ionization energy here, I'm going to get rid of one electron to make it a +1 ion. So now it's beryllium 1+. And then if I add a second ionization energy here, it's going to be a 2+. And the third ionization energy would be a 3+, and so on and so forth. So this is the topic of second ionization energy, or second and third ionization energy as well. And here it says, after the removal of first electron, ionic radius is smaller as electrons are held more tightly, right? So again, let's look at this first. After the removal of first electron, ionic radius is smaller as electrons are held more tightly and more energy is required, right? So remember this topic of ionic radius, and I'll go back up to ionic radius here. Remember here, if I remove an electron, it's going to become a cation, right? I'm going to have a positive ion, right? Remove an electron, I'll have a net positive charge. So they're going to be smaller, right? Smaller than the atom itself. If something is smaller, it's going to be harder for me to remove an electron because the electrons are more tightly held together. It has a more attractive effective nuclear charge with the nucleus, so it's more attractive to the nucleus. So it's a lot harder for me to remove an electron from that atom. So that's how you see this trend here, right? You have the first ionization energy small, and then it's bigger, and then even bigger, and then really, really big, right? So that's kind of my trend here, and I'll write this down for you. So this is write this in black. So we have IE1 is greater than IE2, which is doubly greater than IE3, and then IE4 is this big one here. So again, it increases, and I'll tell you, I'll explain this. So it increases because ionic radius decreases for cations. So meaning that it will be more difficult. And when I say more difficult, I'm saying requires more energy. More energy to remove electron. So that's what it is here. Because it's more tightly bound together, right? So that's the logic behind this here. It's more tightly bound together because it's smaller. Because let me write here, electrons are drawn closer to nucleus. So because if I'm removing electrons, I have a net positive charge in my atom, right? Or my ion, sorry, in this case. So my electrons are going to be closer apart or closer together with the nucleus because it's attracted to the nucleus. If for the opposite case, if I had more of a negative charge, if I had an anion, more of a negative charge, it would actually pull the atom slightly bigger. So if I had less electrons, it pulls the atom smaller. If I have an excess of electrons or an anion, it would kind of expand it. So it would push the atomic radius or ionic radius, slightly bigger. So that's the topic of ionization energy and second ionization energy as well. So we're going to move on to electron affinity. I'm going to give you a second to kind of copy this down while I take a sip of water, but this is electron affinity. So I'm going to write this down, and then if you need time to kind of think about this topic, you can take that time now. So do electron affinity. So take some time to copy this down if you want to. I'm going to move on to electron affinity. So we have here this topic of electron affinity. So again, all these trends are very different from each other. So just keep that in mind. So far we had atomic radius. We have ionic radius is kind of the same thing as atomic radius, where it's kind of determining the size of the atom. And then we have this topic of ionization energy. So the energy needed to remove an electron from the atom. So now we have electron affinity, and they all really sound the same, right? So you make sure you don't get confused when we talk about these topics here. So electron affinity would be, I'm gonna write this down here. So it's energy released when an electron is accepted. So this is kind of the opposite of ionization energy. So I'm gonna write this down. This is the energy released when when electron is added or accepted by atom. And then again, this is also in gaseous state, in the gas state. So what does that mean? So I'm going to copy this down and I'm going to define this again for you. So again, I have an element, and I have an element here. Plus I'm going to accept an electron. So an electron is going to get, I have now an X minus, so an anion, and I get this is the electron affinity, right? So I'm going to define this for you before we start. Again, X here is our element. I am adding one electron, so one electron. So that's this energy released when I'm adding one electron, right? I'm going to get my creative product, which is my anion in this case. And then the energy that's being released when I add an electron to the element is this electron affinity here. Electron affinity. So that's what this chemical equation means here. So again, what this means is that, so if you think about this definition of electron affinity is the energy released when electron is added or accepted by atom in gaseous state, a gas state. Which element or which group would you think would have the greatest amount of electron affinity? Which one would want to accept an electron so that it which of these groups would release the most amount of energy when it accepts an electron? So think about that for a sec. So again, this topic of electron affinity, I'll give you a minute to think about this, is the energy released when electron is added or accepted by an atom, right? So which group of elements would you think, which group of elements would release the most amount of energy when one electron is added? So take a minute to think about that, and then we'll take up the answer. So we're talking about the most amount of electron affinity in this case. So obviously, if I'm releasing the most amount of energy in terms of electron affinity, I want something that's only one electron away, right? Because I'm adding one electron here. So in this case, it would be the halogen group, right? The group 17 has 7 valence electrons, or they're one electron away from creating that full octet, right? So for example, chlorine is electron. If I add one electron in this case, I'm going to get Cl minus, and I get some sort of activation energy, right? Sorry, electron affinity, right? Cl minus is very, very, very stable. And this here, remember I have this is a chlorine here has 7 valence electrons. So it means it wants this electron, right? Which means this electron affinity would be very, 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 very massive here. So I can define a trend now. And what about the least amount? Let me do the least amount first. What energy would what group of elements would have the least amount of electron affinity when I add an electron, right? If halogens is the most here, the least in this case would be the other way, right? The alkali metals, right? If I add an electron to lithium, it's not going to really do anything, right? Let me draw that for you. Actually, let me draw chlorine for you first, and I'll show you why chlorine is a thing. Chlorine has 1, 2, 3, 4, 5, 6, 8, and then this one last shell, it'll have 1, 2, 3, 4, 5, 6, 7, right? And then I'm adding this electron. I'm doing red here, right? This one electron is this electron here, right? So that matters a lot. So if I add it to that, it becomes a stable octet, right? So this is going to emit a lot of energy here. It's going to emit a lot of electron affinity, right? It's a lot of energy being released when I add this electron here. However, let me do lithium. So lithium has 1, 2, and it has 1, right? So if I add electron to lithium, bam, I add electron to lithium, it doesn't make it more, it makes it like slightly more stable, but it's still a very, very reactive substance, right? Again, I need 8 electrons to fill the shell, right? I'm very, very far from this number. So I don't have electrons, I don't have a full shell in this case, which means the electron affinity here is much, much smaller. So small, and this is large. So that means I can define a trend here. My trends of electron affinity. Let me do this here. Trends of electron affinity. So as you can see, this is the least amount, this is the greatest amount. So across a period, it would increase, right? Across a period, it would increase, right? Because I want more electrons to fill up that last shell, right? I want more electrons to make it more stable, and once it makes it more stable, it's going to emit a lot of energy, right? And that's kind of the logic there. And then down a group, it's going to decrease, and I'm going to explain why it decreases as well. Decrease. So let me take a lithium and sodium again. Or actually, let me take fluorine and chlorine. So these two are already high in electron affinity. So because they're both halogens, like I said before. But let me take fluorine. 1, 2. 1, 2, 3, 4, 5, 6, 7. And I'm taking chlorine, right? 1, 2. 1, 2, 3, 4, 6, 7, 8. And then I have one more shell. 2, 3, 4, 5, 6, 7, right? So for example, I'm comparing fluorine and chlorine here, and the the electron affinities. So this here, the red one would indicate my added electron, right? As you can see, chlorine in terms of atomic radius is much bigger than fluorine, right? If it's much bigger, it's going to decrease the electron affinity. And what that means is it takes less energy for me to add an electron. When I add electron, it's going to release slightly smaller energy just because the atom in itself is so much bigger. So what that means is if I add electron here, if I add electron to fluorine, for example, it's going to release a lot of energy because the atomic radius is smaller, right? So if it's smaller, again, I have the attractive forces between the nucleus and the electrons are much higher, right? So if I add an electron here, it's going to release all that you can say tension, or release all those attractive forces into energy. So that's fluorine. And with chlorine, because the atomic radius is bigger, the distance between the nucleus and the valence electron, or the last shell of electrons, are much bigger. If I do add an electron, it's still going to emit a lot of energy, but not as much, because the attractive forces between the nucleus and the electron is slightly smaller. So that's why it decreases down a group. So that's the logic behind this trend here, as it decreases as it goes down a group. So it all comes back to this topic of atomic radius and effective nuclear charge. And I'm using atomic radius, and atomic radius is actually, I say it's the most important trend, because if you don't have atomic radius, it's very, very hard for us to predict the trends of ionization energy and of electron affinity as well. So that's kind of the logic behind here. And this graph here shows that the atomic number is going to increase, right? I have lithium here. It's smaller, and then it dips down for a bit, because there's there's an exception here that we might talk about in grade 12, but it's going to generally grow higher until it hits fluorine and then goes back down, right? Because we jump to the next group here. So that's why I have electron affinity in this case. So again, obviously the least stable amount are noble gases, but alkali metals in this case for electron affinity are also they're slightly bigger, but also as small as well. So so just to review again, as atomic radius increases, the atom has looser hold on electrons, right? So the effective nuclear charge here, but the attractive forces between the nucleus and the electrons are much smaller. So my electron affinity decreases. So that's this example here. And as atomic radius decreases, it has a tighter hold, which means the electron affinity increases. The attractive forces between it increase, which means as I release that energy, it's going to increase as well. So that's those two things. I'm going to talk about electronegativity now, and I'm going to go kind of off this. I'm not going to go off this PDF file here, so I'm going to just talk about that, and that's going to be probably our last concept for today, because I want to review everything that we talked about in terms of periodic trends. Let me talk about electronegativity. So electronegativity. So we talked about atomic radius today. We talked about ionization energy. We talked about electron affinity. So electronegativity. What is electronegativity? So I'm going to define it for you. So this is the measure I'm taking this off a dictionary definition. A measure of the tendency, or how I like to put it, is the inherent property to attract a bonding pair of electrons, or to attract electrons. So what does that mean? So it says here, measure of tendency to attract electrons. So it's the inherent property. So it means that it's not, I'm not adding energy to it. It's just like I'm looking at an element or an atom, let's say lithium, for example. Does it attract electrons? Let's look here. Does lithium here attract electrons in this case? Not really, right? Lithium does not attract electrons. In fact, it's one of the most least electronegative ions, because the reason why is that I don't want to add electrons to lithium. A lithium wants to get rid of its one valence electron. Why would I want to add more electrons to it, right? So in this case, lithium has the least amount of, and I'll use example here. Lithium has the least amount, is the least electronegative. So lithium, Li, is not very electronegative. So I'm going to say less electronegative than, for example, what would have, let's take a moment, take a minute to think about what would have the greatest, what would have the most electronegativity in terms of elements. What would want an electron, right? Measure of tendency, the inherent property to attract electrons. Which element is the most attractive? Why would the electrons want to go towards this element? And this is one electron. We're talking about one electron here. So again, my halogens are, again, if you take a moment to think about that, my halogens actually are highly electronegativity negative. So let's say fluorine, then fluorine. And the reason why is that it's very attractive. It wants that last electron to make the complete energy level. It wants to make that electron stable, right? Or sorry, the energy level stable. So it's very attractive to electrons, right? So in this case, I can say that the trends here is actually kind of the same as my ionization energy, but the trends here, trends in electronegativity would be, erase this would be, if I grow across a period, it would increase, my electronegativity would increase in this case. And I use my example of lithium and fluorine, right? As I go from left to right, fluorine is the most electronegative, lithium is least. It's going to increase electronegativity as I go from left to right? So it increases across a period. And what about down a group? Down a group, it's going to decrease. Down a group, it will decrease. So why would it decrease as I go down a group? So let me look at, and again, this actually goes back to, surprise, atomic radius. So I'm going to look at, let's look at fluorine and chlorine again, actually. And I drew it already. Let's look at these two examples again, fluorine and chlorine. And I'm going to erase these, the one electron here. Fluorine again is extremely electronegativity negative. I need one more electron for me to satisfy the energy level of fluorine right here, right? So it's going to make a full shell if I add one electron here. Same with chlorine. Chlorine is also very electronegative. If I add an electron here, it's going to be a full shell. However, fluorine wants that electron much more than chlorine just based off atomic radius. So based off atomic radius, fluorine, because it's smaller than chlorine, it wants that electron much more than chlorine, or not much more, but slightly more than chlorine, because if fluorine grabs that last electron, it's stable, it's nice, it's also a smaller atom, right? So the attractive forces between the positive core, the nucleus, and the electrons are much greater than chlorine, right? Chlorine is a bigger atom, right? So although once it accepts that electron, it's still electronegative. Once it accepts that electron, it's still good, but the attractive forces between the nucleus and the last shell of electrons are much they're smaller. There's not much attractive forces between the valence electrons and the nucleus here, which means the atomic radius again plays a part in defining our electronegativity, right? So down a group, it decreases, and I'm going to note why it decreases, because increase of atomic radius. Because increase of atomic radius. And what we can do is there's a periodic table, but there's also an electronegativity periodic table as well. And I can show you this one here. I don't know if you can see this, the numbers here, but as you can see, the noble gases are not really electronegative. Some of them are, because don't worry about how wide some of them are. We can get really wonky with noble gases. But if you look at lithium here and sodium and potassium, it's actually, if I go down the group, so down the down the alkali metals group, I have 1, 0.9, 0.8, 0.8, 0.7. So it's gradually going smaller and smaller, right? The numbers are going smaller, right? So it proves here that down a group, it decreases in electronegativity, right? Because I don't, again, the attractive forces between the nucleus and the electrons are much weaker because the atomic radius increases, right? And as you go from left to right, so lithium, beryllium is 1.5, and then 2.0, 2.53, 3.54, right? 4 is actually the greatest electronegativity. So it's the most electronegative. Fluorine is actually the most electronegative ion, right? The top right corner makes it the most. So in this case, because as I go across a period, it's going to increase in electronegativity because the inherent property of the element is going to want more electrons. It wants to satisfy that energy level with more electrons, right? So it becomes more electronegative. So we actually use electronegativity very, very often when we talk about bonding, and bonding is very important in our next unit. When we talk about chemical bonds, ionic bonds, covalent bonds, we can use electronegativity to predict the nature of the bond, and this is very, very, very important. And that's what we talked about. I chose to talk about electronegativity today, whereas some people talk about it later on. So I'm not going to go over activity series because we're going to talk about this probably during next unit when we talk about reactions. But I'm going to review what we did so far with trends, because I'm going to try to draw a mock periodic table for you. So let me try this. So it kind of goes like this, and then it goes like this. Actually, let me center it. Goes all the way here, and then is that no, that's not right. How do I draw a periodic table? Okay, it's kind of like that. So this is my mock periodic table, and I have kind of hydrogen is here, top left corner, and it kind of makes this kind of thing here. So it kind of makes this kind of thing here, like that, right? I'm clearly very, very bad at drawing stuff. And this is hydrogen here, or sorry, helium. That would be helium, and then this one would go up. Okay. So this is my mock periodic table. You can fill it in. This is hydrogen, it's helium, and then et cetera, et cetera. So this would go like this: 1, 2, and then 1, 2, and 3, 1, 2. Yeah, this would be 1, 2 is like this. 1, 2. This is a bit fatter. Sorry, and then it kind of goes. And I'm making these lines, but they're not very, very accurate. And it kind of goes like that, right? So this is my mock periodic table, and I don't really care about how accurate this is, but what it does is I want to actually summarize the trends for you. So the first trend we talked about was atomic radius, right? So atomic radius. So atomic radius, I'll do maybe here. So AR would be atomic radius. So atomic radius, as I told you, atomic radius as we go, actually no, I'm going to start with the top right corner. Atomic radius. As we go down a group for atomic radius, it's going to increase, right? It's going to increase. So I don't know if I can write. Can I write like sideways here? Oh, I can. Let me try to write this sideways. Oh, this is really hard. Maybe if I write here. Nope. I actually can't write sideways with my tablet. That sucks. But let me just do it in a different. I only have 3 colors here, so I'm going to say it increases as I go. So I'm going to say it in blue. It increases. So I'm going to do blue is increase. Atomic radius increases as I go down a group, and as I go across a period, it's going to decrease, right? Let me do it at the top. This will decrease as I go across a period. So that's good. And the reason why was increases greater shells. So I'm adding more energy levels, which means it increases. It decreases because as I go across a period, because there's more electrons in the shell, and it becomes more attracted to the nucleus, right? So as I add more electrons, the nucleus is going to pull the electrons towards itself, so it decreases the atomic radius. That's good. What about ionization energy? So when we talk about ionization energy, remember it's the energy that is, and I'll scroll up here for you to reference it. Ionization energy is the amount of energy to remove an electron, right? So if I'm removing an electron, by ionization energy, it actually increases as I go across a period, right? So across a period, I'm going to do it in blue, would increase across a period. And why does it increase? Because remember, lithium has the least amount of ionization energy, sorry, because it wants to get rid of that last electron, but a noble gas does not want to get rid of any electrons, right? So ionization energy would increase as I go across a period, and as I go down a group, as I go down, maybe I'll do it here. As I go down, it's going to decrease, right? So the amount of ionization energy is going to decrease as I go down a group, because again, the electrons in the outer shell are less attractive to the nucleus, so therefore it's a lot easier for me to remove that electron. So that's atomic radius and ionization energy. And then let's go to electron affinity now. So electron affinity was, if you recall, the energy released when an electron is accepted by an atom in the gaseous state, right? So when it's accepted, so electron, if it's accepted by an atom in the gaseous state. So again, I told you that the halogens have the most amount of electron affinity, and the alkali metals have the least amount, right? So it's going to increase as I go across a period, right? So across a period, it increases. Let me do that in blue. So this is EA. So actually, I'm gonna couple this as well. EA, electron affinity, and ionization energy both increase as I go across a group. And then I have here, if I'm talking about as I go down a group, electron affinity decreases, right? Because again, my atomic radius is getting bigger and bigger. The energy that's being released is much more. It's much smaller because it has a looser. The attractive forces between the nucleus and the electron are much smaller, right? So if I go down a group, it also decreases. So it follows actually the same trend as my ionization energy. So I'm going to write here EA, or electron affinity. Luke asks me, how old are you? I'm actually pretty young. I'm very transparent about my age. I'm actually 24. So I'm actually a relatively young teacher, just coming out of teacher's college. So hence why I'm doing this as well. And then, so we're talking about electronegativity, right? So this last topic was electronegativity, and we talked about how here, transit electronegativity, remember, it's the inherent property in which the element or the atom attracts electrons. So I told you across a period it increases. So across a period it increases, which means this is also, I'm going to say EN as well. EN also increases. And then as I go down a group, it decreases here. So this also decreases. And again, the reason being is that electronegativity, remember, it's the inherent property in which it attracts electrons. As I go down a group, the attractive forces between the nucleus and the electrons are much more smaller, which means it's not as electronegative if I give that element electron, right? But however, if I go across a period, I have lithium who doesn't want an electron because it only has one valence electron. If I get more, it doesn't matter because I'm still 7 away from being a full shell. But all the way to lithium, all the way to fluorine, where fluorine has 7 valence electrons, and fluorine really wants another of the last electron for it to become a stable element. So this is a summary of all the trends in the periodic table. So we have atomic radius, we have electron affinity, we have ionization energy, and electronegativity. So this is a summary of what we did today, and actually last week as well. So just a little, so that brings us almost to 11. If you have any questions, you can feel free to save them for next week or save them the next time I stream. Honestly, I'm pretty open with questions, so whatever you ask, I'll probably answer if it's related to this topic. But what we're going to do next week is we're actually going to finish off Unit 1. Unit 1 is basically almost done. I choose to actually do activity series in the second unit when we talk about bonding and reactions, because I feel like it's more pertinent to that topic. So I'm going to save this, and we'll come back to this activity series and reactivity topic. We're going to come back to this when we talk about reactions, because reactivity talks about when two elements and two atoms combine together to bond to make a new substance. So I'll talk about activity series later on when we talk about reactions. So that actually concludes our unit. And actually our lesson today on units on atomic structure and periodic table. So for the next unit, what we're going to do is we're going to start looking at, I'll give you a sneak peek. We're going to look at chemical bonding. So we're talking about this. Some of you, this might be a review. So ionic compounds, ionic bonds, molecular compounds, covalent bonds. So we did that. We're going to do that. We're going to do some properties, which you might be familiar with, and we're actually going to talk about how do we name chemical compounds. And some of this is great review of grade 10, and some of this would be new for grade 11. When we talk about especially multivalent compounds, when we talk about polyatomic ions, these are much more complicated in terms of naming. So we'll talk about those things as well when we talk about in our next lesson in Unit 2. And I'm going to talk about activity series probably here when we talk about single displacement reactions. So I'll go back to my slide, but we'll make our way there as we move along. So as always, if you have any questions, let me know in the chat for tomorrow. I'm here tomorrow as well, or actually I'm here in an hour doing grade 12 chemistry. So if you want to save your questions then, that's perfect. But if not, again, thank you for watching. I hope you learned, hope you took away something from today's lesson. And as always, yeah, thank you for watching and have a great day.